Yeah, it's my pleasure now to invite Dr. Pravin Bhagwat to chair and host a discussion session that's going to be all about connectivity with our Turing awardee, Dr. Robert Metcalfe. Over to you, Dr. Pravin.
Hello. So, good morning, everyone. And thank you, ACM, for giving me an opportunity to host Bob. And Bob doesn't need any introduction. I think everybody here and heard about Bob when you were studying computer science in your undergrad. He is the inventor of Ethernet. I think one of the technologies in our lifetime which has unified humanity better than anything else. So my true pleasure to be here with you. And my job today is to be as quiet as possible and let Bob speak. But to summarize, I think Bob is a researcher, he's an engineer, he's an entrepreneur, and he's a visionary. So I'm going to try to divide up our 1 hour today to give adequate time to cover each aspect of Bob's personality. And with that, let me kind of begin the conversation to understand the journey of Bob, starting from grad school days. How did you land up at the opportunity where you could invent a technology as powerful as Ethernet? So over to you.
Thank you very much. Good morning. Good morning. Thanks for asking that question. I was a student at MIT, undergraduate, and I graduated eventually, but not before building a connection between MIT and the ARPANET, which is what they used to call the internet at the very beginning. And so I built this card. And I had just learned digital electronics at MIT, so I know how to build that card. And it was my baby step into networking. Then I went to work at Xerox Research in Palo Alto. And of course, they asked me to build another one of those cards, the one I had just built at MIT. So I built one for Xerox. And then the lab decided to build a personal computer. And since I had just finished building these two cards that did networking, I got the job. Think of the job that I got. For the first time in human history, there was going to be buildings full of personal computers with one on every desk. And that's not impressive to you today, but it was really impressive in 1973. No one could figure out why you'd ever want to put a PC on a desk. But that project needed a network, and I got the job because I was the networking guy. So that was perhaps my biggest stroke of luck, getting that job. So I found a man named David Boggs, a grad student at Stanford, and he became my partner, and we built the first Ethernet. And the Ethernet was a 1-year project. I thought it was a 1-year project. It turned out to be a life's project. But during that year, David and I put together, we had a constraint. This is an engineering thing. We had constraints. One of them was whatever we designed had to fit on a card this big with 60 chips on it. And it couldn't be 61 chips because that would be hard to make. So that was a constraint. We had a series of constraints. But the goal was to connect these PCs, and we were building a laser printer. I wrote the operating system for this laser printer. And then they gave me the job of networking the laser printer. This laser printer was a page per second at 500 dots per inch. So it needed a substantial network, so we used the same network for the PCs as the printer. And then the PCs could use the printer by using Ethernet to send their documents over. That was probably the killer app of Ethernet was printing. And Ethernet, what we chose is my answer getting too long?
No, sure. I'll interrupt, no worries.
So I went to the University of Hawaii. I spent a month there. I recommend it. And they had a network called the Aloha Network. And it was a packet radio network. And in that month, I learned two things. One, Ethernet could not use radio. The semiconductors didn't exist. The semiconductors we enjoy today for Wi-Fi didn't exist. We had to wait 25 years for the semiconductors to exist. So Ethernet couldn't be radio. Oh, the radio modem was this big. The PC was this big. It didn't fit on the card, so no radio. That's where we decided to wait for the semiconductors conductors to come 25 years later. And the other thing I learned was the Aloha network had a great method for putting for stations to take turns sending their packets on the network. So we took that technology, that idea from the University of Hawaii. And those three, there were three technologies. One of them was the coaxial cable that we chose instead of radio, and one of them was the Manchester encoding. We put these packets on the coax by wiggling the voltage, but we didn't want to have a global system clock. It was pretty standard then for communication systems to have a global clock, and they're a pain in the neck because you're always having to synchronize them. So we used Manchester encoding, which put the clock in the packet. Each packet carried its own clock and clocked itself into the shift registers. And then the third technology we had was as I just mentioned, the Aloha network. All three of those technologies are gone now. So Ethernet has blossomed without those three specific technologies. And what's replaced those three, and now I'll stop. Ethernet brought packets to the desktop. And we didn't really notice how important that was. But before Ethernet, the packets would stop at the computer center in the host, and then it would run the apps over there, and then it would talk to you through a dumb terminal. But with Ethernet, the internet packets would come in and be forwarded to them if properly addressed. And so you had the internet, you could write computer programs to develop applications on the network. A good example of that would be the World Wide Web. You know, the World Wide Web was put on top of this plumbing, this Ethernet plumbing. The second thing Ethernet did was to introduce bandwidth abundance. The Ethernet, the Xerox Ethernet one on my desk was 10,000 times faster than the network that it replaced. Not 10%, not 10 times, 10,000 times faster. And so after Ethernet, bandwidth was considered not so scarce anymore, but abundant bandwidth. And then the third thing that Ethernet contributed to was it joined the list of standards. The internet was really a standards initiative. And at the bottom of all the TCP standard and the IP standard and the FTP standard and the HTTP standard, at the very bottom there's an Ethernet standard. So that was the third thing that Ethernet did. Is that enough of a, that's kind of a long answer, I'm sorry.
No, good. So I'm curious, at that time, some of the decisions that you took were a function of the constraints you were dealing with in terms of technology, what silicon was available. But a naive way of thinking about building local area network is to kind of create a TDMA system and have people go in each slot. But Ethernet is very different. It has taken a very radically different approach to doing it. So how much of the design was a result of deep thinking about how this protocol needs to be designed versus something that was a result of the constraints that you're dealing with from a technology standpoint? Because this technology has survived for a very long time. I mean, usually we are living in a world where things become obsolete in 3 months. And here we are sitting 50 years later, the technology is still going strong and progressing. So something deeper about the design that is there, why it has withstood this test of time. So I'm curious if you want to reflect on what are some of those core design principles in it.
Well, instead of the idea of carrying information in packets, a series of bits, a destination, a source, a packet type number, a checksum, that's a packet. That was not an Ethernet idea. That was an internet idea. That was an ARPANET idea. So the tone had been set. We were building a packet network, and all the communications would be organized around packets. In fact, we later discovered it would be two levels of packets. There's the packet, when you send a packet, it has a local destination over there, but it has an ultimate destination, which could be around the world. So there's really a two-level internet packet structure. Ethernet didn't invent that. Ethernet fit into it. And so Ethernet carries those packets for higher level protocols. And as to the durability, you mentioned TDM.
Yeah.
It was, for a couple of decades, it was my life's goal to remove all TDM from the surface of Earth.
So maybe, yeah, let's hear about
It was called SONET, and it was synchronous optical networking, and Ethernet went after SONET, and I think we won. I think we've killed SONET competitively.
And why? Why above TDMA? What's wrong in it?
Two things, no, probably 10 things, but two that I can think of. One is the TDM allocates bandwidth over long periods of time, even when it's not being used. So you're on the telephone and you stop talking, TDM is still wasting bandwidth. Whereas if you stop talking into a packet phone, it stops sending packets because it doesn't have anything to send. So part of it is multiplexing and compression. But another benefit is switching. So the switching rate of a TDM network, that requires round trip, opening of a connection, closing of a connection. But the packet switch mechanism, you can switch packets in different directions per packet. And that, of course, enables things like Google and Facebook that have tens of millions of people coming at them at the same time. The switching function, that is, of getting the packets to talk to that machine, now that machine, now that one, is built into the packet scheme.
So changing the subject a little bit, tell us a little bit about your days at Xerox PARC, because as students of computer science, we hear so many great innovations coming out of that center. What was it like to be in that place at the time when some of those technologies were being invented? And how much of do you think being in that environment makes a difference? Because you remarked that you were at the right place at the right time. That was one of the key things. I'm curious to know, in addition to that, how much does the environment plays a role in kind of making the person the way the person is?
So my version of a longer answer to that begins with a man named Robert Taylor, a Texan, I might add, and a graduate of the University of Texas. And he got a job managing the computer science research of ARPA. So he was the guy giving ARPA grants to all the computer scientists in the world. And one day, he got recruited away from ARPA to Xerox. So Xerox was a copier monopoly and had lots of resources, and decided to build a lab, a new lab, to develop the paperless office of the future. And did some research, decided to put it in Palo Alto, decided to get Bob Taylor to come and build it. And since Bob Taylor knew all the computer scientists in the world, he was especially good, present company accepted, in picking out the good ones and recruiting them to come to Palo Alto.
So he found you and asked you to come over to PARC?
Yeah, that's right. Actually, he did more than that. So I got a job offer from Xerox. I was working on my PhD at Harvard. I submitted a draft of my dissertation, got the job at Xerox. My wife got a job. She left MIT, got a job at Stanford. My parents were ready to come to Harvard Yard to see their son get his PhD. And I failed my thesis defense a week before commencement. It was horrible. But I had to call up Bob Taylor and tell him that I failed. Hi, Bob. Didn't get my PhD like I hoped. And he said, Dad, why don't you just come out here and you can finish it while you're here? He saved my life. It was his principles of management of research that made the success that you asked about. he was a very he wanted Xerox PARC to be like a university laboratory, and most of the researchers at Xerox PARC were Stanford professors, including me. And so I think he judged properly that being near a university was important. And he had a very light touch. I'll tell you one story where we were having, David and I working on Ethernet, were having trouble getting it to work. We were debugging it. And we had an adversary in the lab who shall remain nameless. He and I hated each other. And he saw that Ethernet was not working. So he announced, and he was way senior to me, he announced XNet. He was going to do XNet. And this was very bad news because he was going to suck all the oxygen out of the lab and kill Ethernet. And his XNet was 16-bit parallel, 32 wires in a cable this thick. It was a bad idea. So I went to Bob Taylor, crying, make him stop, make him stop. The next day, XNet stopped. So I go to Bob Taylor, I say, hey, thanks a lot for killing XNet. It was a really bad idea. He said, oh, I didn't do that. I didn't kill XNet. 30 years later, I got him to admit that he actually had killed XNet, but he didn't like killing it. It was a violation of one of his, it was too heavy-handed. I think the thing that pushed him over the top is that this was really a bad idea, born of revenge. The two of us hated each other, so he came up with XNet, not because it was a good idea, but he was attacking me personally. And Bob put an end to that. Anyway, my general answer to your question is Bob Taylor. A slight elaboration, you just had Palo Alto and Stanford, and Bob's access to the best computer scientists in the world that led to this beautiful place.
Actually, Xerox at that time came up with some amazing inventions. I mean, the whole personal computer, mouse, the LCD screen, Ethernet. But we all know that none of these could be commercialized inside Xerox. People had to kind of step out to really build businesses around it. So maybe throw a little bit of light that why an institution which was so successful in fostering such great ideas couldn't take it to the commercial success.
Well, there's a double-edged sword called monopoly. And I've already mentioned this. I should have mentioned Xerox was a copier monopoly and had a lot of money. And that enabled it to create this lab. So in that case, monopoly was enabling. But then when the products came and we tried to enter the computer market, we had a company that was a monopoly entering a fiercely competitive marketplace. And the market just chewed us up and spit us out. I mean, it was, so that's my answer. Monopoly, the double-edged sword. Monopoly made this thing possible, but it also made it hard to compete once we had real products. My colleagues that I work with like to use the third person. They like to say they failed to commercialize. They did this and that. And I have to remind them, wasn't that us? Weren't we there at the time? Weren't you in charge of that? No, Xerox failed to capitalize. By the way, Xerox did capitalize on a lot of them, just not, it didn't turn out to be Apple or Google, but it was still I think a successful venture. It should not be used to discourage corporate research.
So tell us a bit about what prompted your exit from PARC and when did that happen and the story of starting 3Com and commercializing this idea of Ethernet.
So I arrived at Xerox. I graduated I got my PhD from Harvard. Of course, it took an extra year, and became a researcher. And so for 4 years, I was in the Xerox Palo Alto Research Center in the computer science lab. And then I left that to join Xerox System Development Division to commercialize the products we had developed in research. And I did that for 4 years. Oh, I left Xerox twice then. I left Xerox after the first 4 years, and then I left Xerox after the second 4 years. And there's good learning there. When you leave a place, don't slam the door behind you. You'll be back. And I was back. Twice, actually. I came back after leaving the first time, and the second time I won Xerox as a customer for my startup by not slamming the door behind me as I left. And so now to your question, why did I leave this? I left the first time because all my friends were making more money than I was, and it was and they had MBAs, mere MBAs, and they were making more money. So youthful person, I left Xerox and increased my salary by 25%. But I hated the new jobs. I only lasted 7 months, but I convinced Xerox to recruit me back. And of course, when you recruit somebody, you have to pay a premium. So I got a 25% raise coming back. So I got a twofer. I got and this at Xerox, this was called a Metcalfe. You're pulling a Metcalfe. You leave to increase your salary, then you come back and get an increased salary. It's called a Metcalfe in employment
Has
technology.
anyone played Metcalfe on you at 3Com?
Well, I tried to fight this Metcalfe strategy at 3Com. At 3Com, it was our policy that everybody should be competitively paid. It was our job to be sure that all our employees were competitively paid. And if they got a better offer, we would not respond. The principle being this employee is already competitively paid. He's getting this silly offer from somebody else, and we're not going to match that. That was our policy, and I think it worked pretty well. But it did put the onus on us to be sure that our employees were competitively paid.
So tell us the story of 3Com. How did 3Com start? And
Okay, so when I left Xerox the second time in January of '79, the memo said, I'm leaving Xerox, quote, to pursue entrepreneurial ambitions, with no clue as to what they were. And in February of that year, '79, I had a meeting with Gordon Bell of the Digital Equipment Corporation, and he wanted an Ethernet for the second largest computer company, DEC. But I declined to do that, and instead got him talking to Xerox about using Ethernet to connect DEC mini computers to Xerox printers. And pretty soon we had the idea called DIX, D-I-X, DEC, Intel, Xerox, to build an Ethernet that would use Intel semiconductors to connect digital computers to Xerox copiers. And then the US government came in and said, you can't do that. It's a violation of antitrust law. You cannot be in the same room. It so happened that my roommate in college was an antitrust lawyer, Howie. So I called up Howie, presented him with this challenge. I wanted these companies to meet, but the lawyers wouldn't let them. Howie gave me a checklist of how the meeting could be arranged. And one of the key features was if you were meeting to create an open standard, that was okay. So no marketing people were allowed in the meetings. There needed to be a government observer. And you had to be working on an open standard. So then we didn't go to the ACM, we went to the IEEE and created project, I don't know why. Does ACM have standards? No. Oh, so that explains it. Not yet. Oh, 4.0, who knows? So we created Project 802 at the IEEE to standardize the DEC Intel Xerox Ethernet. And that IBM, meanwhile, noticed this. So IBM was announcing it, as it usually did in those days. It would just announce products. And it had announced SNA, System Network Architecture, which was completely proprietary. And by the way, I used to call it SNA, just to annoy IBM. But IBM noticed that customers were liking the idea of having a multi-vendor LAN standard, local area networking standard. So they said, we better have one too. So they ran off and they found one called the token ring, and they showed up at the IEEE, and that started a huge war that lasted 20 years as these standards competed. The IEEE caved and standardized Ethernet, token ring, and token bus. So there were 3 IEEE standards. We killed token bus very quickly, but it took us 10 or 20 years to kill the IBM token ring.
Did Apple Talk have any role to play around that time at all, or was not in the play?
In June of '79, I got a call from Steve. Had a company called Apple in a city called Cupertino, and I'd not heard of any of those 3 things, including Cupertino. It's kind of funny. It's not that far from Palo Alto, but I'd never heard of Cupertino. And this kid needed a networking expert for he was making PCs. So I declined, but he helped me build my company. Wait a second, what question am I answering?
Yeah, I said, did Apple Talk have a role to
Yes.
play in that time?
So I turned Steve down and presented him with a proposal of a network that I would sell to him. And I called the network Orchard. Get it? Steve didn't get it either. But he helped me start the company. He did not buy any orchards. And I didn't get him to adopt Ethernet until after the next computer had Ethernet, and so did subsequent Apples. So it was a hard sell. So he recruited the guy who worked for me at Xerox, Bob Belleville, and Bob then built the Macintosh. And they needed a network, but Bob Belleville wanted to use a standard chip. While we were waiting to build Ethernet chips to run at 10 megabits per second, there was this much slower existing standard product, and it was fast enough, and that was called Apple Talk. And it competed with Ethernet for 10 years.
So 3Com, when was it incorporated as a legal entity? And
3Com was incorporated on June 4th, 1979, and became part of HP in 2010.
so when I was reading about 3Com, what surprised me a little bit, I would imagine you as a CTO or CEO of 3Com, but you are running sales. So I'm curious, what sort of prompted your transition from a Ethernet inventor to actually driving the sales in an organization?
So we raised some venture capital, we built some products, we started selling them, and yet we were consuming cash. And this is a familiar chart. Cash, like this. And down here is 0. And when cash hits 0, all sorts of bad things happen. Never do that. So 3Com was going like this. So the board of directors of our company had to do something. And by the way, I recruited all of them. They were really great people, and they announced that I was no longer going to be the CEO of my company. Instead, I was going to be VP of sales and marketing. And take that as a measure of how desperate we all were. They took the engineer and made him head of sales and marketing. But the thought there was networking was high tech and very technical. And I could get an appointment with the VP of engineering of a customer because I invented Ethernet. So the idea was make me the head of sales and marketing, and then I could be successful selling. And I don't know if you're familiar with this, but that would be called a bad decision with a good outcome. It succeeded. So 2 years later, we went public with $1 million. I got us to $1 million a month. And I learned how to sell, and I learned how to run a sales
Especially
organization.
if you're selling a vision, you're trying to convince something that people have not imagined or they can't think about. You have to be almost an evangelist
Yep.
to really get that idea across, especially at a time when people didn't fully understand what value a network could bring.
Right. Ethernet was designed to network personal computers, and the problem was there weren't any. So we sort of, all of us had to wait for the PCs to come, and IBM came to the rescue with the IBM PC in August of 1981. And then we put all those we developed the capability of putting all those IBM PCs on an Ethernet a year later in September of 82. And then we went public in March of 84. So it was really, there's IBM has another role in this story, which is they saved the day by introducing the IBM PC. And thereby making Bill Gates the richest guy in the world.
So tell us the story of Metcalfe law, because I think that was invented when you were running 3Com, right? What are the circumstances where that insight came and?
Okay, so we're selling cards that plug into PCs to put them on a network. And there weren't any PCs. So we made a trial. We wanted to make it easy for people to try this. So we made a 3-node network, 3 of our cards, a length of cable, and a diskette for $3,000. The customers would then put PC string cable along the 3, and then load the diskette software into each one. And then the 3 PCs could share a disk or share a printer or exchange email. And we sold a lot of these. People were curious. But then they reported back that this configuration worked, but it wasn't useful, which is seriously bad news for the VP of Sales and Marketing. So I went over to Stanford University that night, and I found the PC that we Xerox had donated to Stanford, and I used it to make a slide. And the slide said, the cost of the network is linear like this, but the number of different connections you can make goes up as the square, like this. And that there's a crossover point here where the value begins to exceed the cost. And then I made 6 35mm slides because there was no PowerPoint. I was on the board of the company that did PowerPoint, and we sold it to Microsoft in 1987. This is 1981, 82. The slide said, the reason your network is not useful is that it's not big enough. And the remedy for that is to buy more of our products. And they did. And we went public on that basis alone. And the value was there. I mean, these networks panned out. It was a risky thing to try, but they worked, and they proved to be useful. So the question arises, since I was head of sales and marketing, was I lying when I made that slide? And the answer is I wasn't lying. I had been at Xerox for 8 years in that future with local area networks of personal computers and laser printers and all that, and we could see that that was good. So we weren't lying when we started selling our products. We knew that they were valuable.
So if I hear your story until now, you spend some few years of life in a research environment, inventing, creating things, and now you're out in the market trying to sell, survive, bring in revenue, which sounds like a much more intense journey. So given the 2 phases of your career, if you had to contrast, which is the one that you really, I mean, for our new students and aspiring entrepreneurs and researchers, what's sort of the lessons learned from these phases? And because we were discussing over breakfast, you said, especially you had a remark about the entrepreneurial phase that do it at your own risk. So,
well, now that you asked, there's sort of 2 ways of living. A research scientist doesn't have alarm clock, gets to work in time for lunch, writes papers. It's a nice life. When I was at Cambridge, England, I was there for a year. And breakfast becomes morning coffee, and then it's lunch. And then lunch becomes high tea, and then high tea becomes dinner. You spend your whole life eating all that. And then over here is the life of a salesman. And it's fierce, it's competitive. It's bad for you physically. It's costs you a marriage or two. But you're changing the world. You're having impact, and that feels good. But you can't compare those two lifestyles. They're just different. So I'm lucky I got to do both. Oh, so the key that I learned, and I had to make that transition from engineer to salesman, there's a secret thing I know I'm going to share with you right now. Selling. Success, I found success in that role by learning how to sell. And I hadn't really learned how to sell prior to that. I didn't take, selling, I didn't get an MBA, and I didn't take sales skills. I learned how to sell in front of customers. And now I can tell you the secret of selling. This is very hard for me because I talk a lot. And the secret to selling is listening. And so, Bob, stop talking. And I learned how to do that, how to stop talking, like right now.
Yeah, I think we will change gears a little bit. Now, story has reached up to 3Com, company is successful, gone IPO.
Okay, so in 1999, my little company, without me, I left earlier. I left in 79. My little company was worth, inflation adjusted, $70 billion.
Wow.
But I should point out it only stayed there for a few days. And then the internet bubble burst and all the stock prices went like this. But the company really, that whole generation of networking companies, Cisco and Juniper and others, boomed during this period. And then, and they're still there.
Yeah.
The bubble burst, but they're still there.
Yeah. Then 3Com was at the right place at the right time in some sense. I mean, when the internet was really booming, could it have become the Cisco?
Cisco?
Yeah, because
Yeah, Cisco's a special case. Cisco was founded the month we went public. One of our board observers, who was on my board of directors for years, a venture investor, resigned from my board and went on to the board of Cisco, this brand new company that was starting. And 3Com was bigger than Cisco for a very long time, years and years, and then Cisco just blew past. And John Chambers did that. John Chambers knew how to do something that I've already mentioned. He knew how to sell. And he sold those Cisco routers, and they blew past 3Com. And 3Com was a multi-billion-dollar company, but it wasn't Cisco. Right. And so we ended up as part of HP.
So I was looking at your Turing Award lecture, which you gave some time ago. And that lecture actually starts with you taking a very bold kind of a statements about connectivity as the key thing, which has emerged out of Ethernet. So next few minutes, let's, I think, spend some time, kind of help us, bring us to that level of understanding of where do you see connectivity moving, what lies ahead in the future, and help us sort of get to some level of understanding which you've already arrived at through your own thought process of the connectivity as a paradigm.
Well, let me first thank the ACM for giving me the Turing Award. I'm humbled, and I take it as an opportunity to be more dignified and well-behaved and do God's work. So thank you, ACM. Thank you. But then I then knew that I was going to give this Turing lecture, and I decided, by the way, although ACM doesn't know this, I have planned to give the Turing talk 50 times. and I've only done it 10 so far, so I got 40 more to go. And it had to be organized around the major learning that I did in the career leading to the Turing Award. Yeah. And I concluded that and here, this is a sentence, I wouldn't change a comma of this sentence. The most important new fact about the human condition is that we are all now suddenly connected. And a lot of what's going on in technology and in the world can be explained by the features of connectivity and how the system is related. So the internet is continuing to boom, and we're now making the transition from the megabit internet to the gigabit internet. It's happening right now. But then when you look into the story of connectivity, you discover it's full of surprises. And the talk is about enumerate some of the surprises of connectivity. And that means the surprises are not going to end now, they're going to continue. So we have to be prepared. When you work in connectivity, you have to be prepared for surprises. Just as an example, a man named Herb Grosch, may he rest in peace, worked at IBM, and he had a law way before Metcalfe's law. And his law said, in essence, bigger computers are better. And he had a chart that showed all the IBM mainframes on a graph, and it showed their costs going up as the square root of the power. Bigger computers are better, and that law was adopted by IBM and by DEC and by Data General and by all the East Coasties. Meanwhile, there was another law called Gordon Moore's law, which basically said networked PCs are better. And Gordon was right, and Herb was wrong. And so Silicon Valley moved from Boston to Palo Alto. In fact, I think it was on the same plane that I took from Boston to San Francisco. I think Silicon Valley was sitting right next to me. Where was I? Oh.
Yeah. So explain the whole connectivity, that it brings about disruptions.
Okay, so
yes.
Turns out not all connectivity is internet. There's other kinds. And one of my favorites have you heard of this new buzzword, AI? Have you heard of that, AI?
Yeah.
So I'm arguing that AI is not the thing. Connectivity is the thing. And the way I make that argument is to show how it's connectivity that makes AI. Neural network. Oh, network, that's a connectivity word. And there it is, right at the core of AI. So then you look at there's a paradox in there that I call it the transistor neuron paradox. Neurons are huge and slow, and transistors are tiny and fast. Let me put some numbers there. Transistors are 1,000,000 times faster than a neuron, and they're 1,000 times smaller. And here's the paradox. We build human brains with neurons, those clunky old neurons, and we have not figured out how to build anything nearly as smart as this with transistors yet. So that's the paradox. And what explains the paradox? How can this be true? How come we can't do better? And the answer is connectivity. The networks are not connected enough. So the chat GTP4 has 176 billion parameters or connections. They're analogous to synapses in the brain. 176 billion. And we're not close to AGI with that. And it's arithmetic will point out why we have 10 to the 11th neurons, each of which has 10 to the 4th synapses. So that's how the neurons win. The connectivity of a neuron is enormous with its 10,000 on average synapses. So we're going to have to increase. My theory is we have to increase the connectivity now of our networks. So I asked OpenAI, will your next GPT have, say, 100 trillion connectivity? And of course, they said, we're not at liberty to answer that question. So my theory is connectivity is going to lead the way in AI. And as we
But actually,
add
this connectivity that you're talking about, do you think Ethernet can evolve to meeting this need? Because this seems to be a very different type of connectivity, extremely high interconnections, because Ethernet architecture is still very much now a central switch with spokes coming out. Maybe some fundamentally new technology or approach is needed to attempt something like this.
Well, you raised one question which I've sort of not made much progress on, but is some form of Ethernetish connectivity applicable to the neural net?
Yeah.
In other words, can neural nets begin to communicate by switching packets through their trillions of connections? And I don't know the answer to that. Certainly there'll be connectivity. As to whether it bears any resemblance to the Ethernet, I don't know.
So I think at this point, I want to kind of maybe open the floor to some audience. If they have any questions that they want to pose while we kind of continue our conversation.
My question is, what motivated you to do a master's degree in applied math coming from an industrial or engineering background, and how did it help you in future? Thank you.
Thank you, but I still didn't hear you.
I think the question is what motivated you to do a master's in applied math?
Yes.
And then later,
How did it help?
yeah, how did that training in applied math? Are you an applied math student by any chance?
I'm pure math, but I'm doing my graduation.
So what was the question?
Question is, what motivated you to do a master's in applied math?
Oh,
And how did that help you to do what you ended up doing?
to make a long story short, in 1969, when I graduated from MIT, MIT called computer science, called it electrical engineering. So I have a degree in electrical engineering, which is equivalent to a computer science degree today. Harvard, on the other hand, called computer science applied mathematics. So everything I did was computer science. It just had different names depending on what school you were at. And eventually they figured out, Harvard hasn't figured this out yet, but so my master's degree is not only in applied math, which is not quite right, it's also in Latin, which is wrong too. Whereas my MIT degree at least says electrical engineering, period. So it was just a naming thing. And the applied math there was, we for example, proved theorems about Turing machines. And we did recursive function theory and lambda calculus and Turing computability. And but to be honest, at the same time, I'm down at MIT building this card with 60 chips on it with dual inline packages and voltages and stuff, while taking the applied math courses. And it worked out very well. I needed both skills to do Ethernet.
Actually, one question I want to ask you, if I look at the trends these days, most of the computer science undergrads are finding great jobs right after their undergrad. And there's a startup culture is also on fire. So there's an urgency to get out there, build a company and be out in the real world. The number of people who really want to pursue masters and PhD is kind of declining. And I'm curious, what is your take? Because it's a investment that people have to make to kind of go through that grind, which prepares you in a certain different form and shape. And having seen now the trend of the last 50 years, what's kind of your advice and take? What is the right thing to do?
That depends on who you are and what you're interested in doing. But to go to my case, so my parents were prepared to pay for my college education. And MIT was $1,700 a year. And so my parents wrote checks for that, and I made it a priority to relieve them of that responsibility, so I went and got a job. So I didn't wait till I graduated. I had a job sophomore year at MIT, and it was midnight to 8 every day. I had a full-time job out in Wayland, Massachusetts. Then I would go into MIT during the day and take the MIT courses. So I jumped the gun. I was 40. I had a job all through college, and I think I learned as much from the job as I did from MIT. Did I answer your question yet? I'm not sure.
No, so I think you're saying it's very much depends on the person in terms of whether
Yeah.
they want.
So the numbers should decline.
Yeah.
We have too many PhDs. No, and here's how you can tell. There's a thing called a postdoc. You know what a postdoc is? You go to get your degree, and then for a year or two, you're a postdoc somewhere. Well, not anymore. Postdocs are 2 years, 3 years, 4 years, 5 years. What's happening? What is happening? Well, all of those PhDs want to be professors, and there are no professor jobs available, so they're queuing up. There's just a lot of them. So maybe fewer of them is a good thing. Do you know what postdocs are really good at? Starting companies. So as a venture capitalist, the postdocs have just finished getting their PhDs, they have their dissertations, they've mastered something. There's a good chance you could make a company out of it. So that's how I see how we navigate out of this crunch that we're currently in.
So yeah.
Hello, sir. Thank you for the insightful talk. I'm here. Yeah. My name is Ritvik. You mentioned in the end part of the talk about a buzzword called artificial intelligence. So my question is, what part of artificial intelligence amazes you, and where the field can improve?
In 1968, I wrote an undergraduate thesis for my advisor. My advisor is a man named Marvin Minsky, who is one of the founders of AI. And my thesis was called A Neuron Model and Some of Its Information Processing Capabilities. All copies of that dissertation have been lost, alas. But the point is, I've been watching AI come and go since '68. And it does come and go. And we're on another wave of it. Here it is. The machine learning wave of AI is now upon us, and it's great. But by the way, do you know what was the buzzword just before AI? Does anyone remember? Consensus, distributed consensus machines. Blockchain was the word. Do you remember you couldn't go to a conference that wasn't about blockchain? Well, when's the last time you used the word blockchain? Anyway, the same thing's going to happen to AI again over time. But the thing that's going to save AI this time is the internet, connectivity. Because AI needs data. And where's it going to get its data? It's going to get its data through connectivity, through the internet. So I'm optimistic about AI. Even if the buzzword goes away, there'll still be AI. So that's an important lesson, by the way. The buzzwords go away, then the actual real thing may still be there.
So thank you, Bob. I'm getting signals from all around that our time is up. Maybe one more question.
So just a comment that you mentioned about too many PhDs and too few jobs. That's certainly not true in the Indian context. The last couple of days, we had, people from universities and industries coming saying, we want PhDs, please come join us. So I just want to make that comment, at least, yeah.
I stand corrected then, at least in the Indian market, yes.
So one question I have is that I was reading a book on some book on super recursive algorithms. So they were talking about some algorithms which needs some machine more capable than Turing machine. And they mentioned there's something called distributed computing, like when there's a multiple computers connected through the network, and to model that structure, to write a generalized algorithm for like a distributed computers, we can write algorithms which cannot be solved in the Turing machine model. So like Can you, like, anything in this?
That's a question that really can't be answered on a stage. We have to sit down with a pencil somewhere.
Okay.
But thank you for trying anyway. I'm sorry, I can't answer your question. We're done, right?
Yeah. So Bob, I thank you very much. And Bob is going to be around over lunch. It's full of so much of wisdom and stories. I think we could capture only a few of them. So there's many more, and I'm sure as you meet him over lunch breaks, some more of this will come out. So thank you very much and enjoy. Yeah.
Yeah, thank you. Please stay on for a minute, if it's all right. As a small token of appreciation, a tamarind tree, has been planted in the name of our Turing awardee this year. And thanks to connectivity, there is a QR code here that can be used to track the growth of the tree. I now request Dr. Pravin to hand it over to Bob, please.